Hi, everyone. In this video, we're going to discuss what is a conservative field and what is a potential function. So let's take a look at this field. So we have a field f, which is a function of three variables x, y, and z. So let's label each component. So this is going to be m of x, y, z. So that will be our function m. Then this will be our function n, and this is p. So you can label them however way you want. I'm going to label them accordingly. Now, to check that this field is conservative, we need to do the following. So I hope you remember that a field is conservative if the gradient of some potential function little f is equal to the vector field. So if you look at this field, it is given in terms of m, n, and p, but they're really our first partial derivative of that potential function f. So you can think of it as m corresponds to, so this is really a partial of f respect to x, and n corresponds to partial of f respect to y, and p corresponds to partial of f respect to z. So those are the first partial derivatives. And we want to test if this is conservative. And the way we're going to do that is by using Clairaut's theorem. We're going to show that the mixed partial, the second mixed partials, are equal to each other. All right, so first we're going to show that we take the first partial of f respect to x, and then we take the derivative of that respect to y. So that's the second partial derivative of f respect to y. We want to show that this is equal to partial of f sub y respect to x. So what we're really doing is we're taking the partial derivative of m, because that's our partial of f respect to y, and then we take the partial derivative of that respect to y. We want to show this is equal to partial of f sub y. So that's this n. So take the partial derivative of n respect to x. So that's our one of the first second mixed partial derivative. In other words, in simplified form, you can show that m sub y is equal to n sub x. Then second, we want to show that our f sub y z is equal to f sub z y. So this can be also written as partial of, now f sub y is n. So that means we're going to take the partial derivative of n respect to z. I'm going to check this is equal to, so f sub z is p. So that means we want to show that this is equal to partial of p respect to y. In other words, in simplified form, you can show that n sub z is equal to p sub y. And lastly, we're going to show that partial of f respect to x, then we differentiate that respect to z, is equal to partial of f of z, and differentiate that respect to x. So in other words, you can show that, so partial of f respect to x, that's m. We take the partial of m respect to z. We show that that is equal to partial of f respect to z, that's p. So partial of p respect to x. In simplified form, you can write this as m sub z is equal to p sub x. So these are the component tests we're going to perform in order to show that the field f is conservative. So for this particular example, so I'm just going to go ahead and copy this, put it right here. And then we're going to do our check. So let's check. So we know that this is our m. We know this is our n. And we know that this is going to be p. So let's go ahead and take their partial derivatives. So we want to test if m sub y is equal to n sub x. Let's check. So take the partial of m respect to y. We're going to get 2x. And then we're going to take partial of n respect to x. That's going to give us also 2x. So this is check. Now we're going to check if, so the next one is, so this one, let's go ahead and do that order. we want to check that m sub z is equal to p sub x. So m, let's take the partial derivative respect to z. Well, that's going to give us 0. And then we're going to take the partial of p respect to x. That's also going to be 0. So this is also checked. They're equal. And the last thing we're going to check is this one right here. Partial of n respect to z, is that equal to partial of p respect to y? So we're going to take the partial of n respect to z. So that's this guy right here. That's just going to be taking the derivative of this component. So that will be 2y. So this is actually partial of n respect to z. That's 2y. And now I'm going to take the partial of p respect to y. That's also 2y. Huh, that's nice. They're all equal. All right, so by doing the component test, we have being able to establish that our field F is conservative. So this is if F has 3 components. If your field has only 2 components, then all you have to do is check this one. That will be it. If partial of n respect to y is equal to partial of n respect to x. All right, now since we found it is conservative, then of course we can find this little f right here, because the gradient of that little f is equal to our field. So we're going to compute that gradient, the little f, which is your potential function. So let's go ahead and do that for this field. So I'm just going to go ahead and copy this down one more time. So now for this field, we're going to compute the potential function. So let's start off with the following statement. So we know that our f is given as these component-wise. This is really equal to partial of f respect to x, partial of f respect to y, partial f respect to z. Those are the first partial derivatives. That means if I want to obtain little f, I will have to integrate these pieces. So I'm going to show you how to do that. So if I simply start with, let's say I'm going to start with this one right here. So I can simply take that function. So to find little f, we can simply integrate partial of f respect to x. That is going to give us what our function little f of x, y, z is. So I'm going to go ahead and do that. So we take the integral of f sub x. Well, f sub x is this term right here. So there'll be 2xy respect to x. So if you integrate this respect to x, y is treated as a constant. So this is equal to just 2x squared y over 2 plus a constant. And instead of putting a constant, you're going to put a function of y and z, since those are the components you haven't used up yet. So they're right here. So I put a function of y and z. All right, so by simplifying this, we know that our potential function f of x, y, z is equal to x squared y plus h of y, z. Now here to find this function, so initially you need to find this function. To do that, well, we're going to take the partial derivative of this respect to either y or z. You can do it in any order. Let's go ahead and find the partial of this respect to y. So let's go ahead and now find partial of f respect to y. So that will give us, I'll take the derivative respect to y. So you'll have 2. No, so I'm going to go ahead and take the derivative, partial derivative this respect to y. It'll just be x squared plus h sub y, or partial of, let's just put h sub y of y comma z. Now I know partial of f of y, well, that is equal to here, this component. So I'm going to set it equal to that. So let's go ahead and do that. We're going to set it equal to that. So I can solve for h sub y. So this is equal to x squared plus 2yz, because that is my partial of f respect to y. Now, once I have done that, I can now go ahead and solve for this function. So we're going to go ahead and simplify. So you'll see that x squared will cancel out. So this will reduce to h sub y of yz. You can write that if you want to. Let's just write it this way, 2yz. Now to solve for h, we're going to integrate both sides. So that means h is going to be equal to if I'm integrating, so I'm going to integrate 2yz respect to y, and this will give me respect to y. So this is going to be 2y squared z over 2 plus, now since I haven't used up the variable z, I'm going to put in a function of z as my constant. So then this will give me my function h of yz. This is equal to just y squared z plus g of z. Now this is what I'm going to replace right up there with f. So this is what I'm going to replace back in here. So my potential function f x, y, z is equal to x squared y plus y squared z plus this function g of z. So the last piece we haven't used up is this term right here, partial of z, partial of f respect to z, which is this term right here. So now I'm going to go ahead and take the partial of f respect to z. So then I'll set it equal to that. So you'll have partial of f respect to z. So the first term is 0. The second term will just give you y squared plus g prime of z. And then I'm going to set this equal to f sub z, which is from the original f sub z is this term right here, y squared. I'm going to set it equal to that. This is equal to y squared. And then again, you'll see that y squared will cancel out. So you'll have your g prime of z is equal to 0, or you can call it a constant if you want, which means g, by integrating, g function of z is just going to be a constant function. All right, so that means now we're ready to substitute this back into our potential function. So our potential function, I'm going to substitute this right in here, and we have it. So our potential function for this particular problem, for this field, is going to be f of x, y, z is equal to x squared y plus y squared z plus a constant. So there are infinitely many potential functions. All right, so that's one way to get it. Now let me show you a quicker way to get to the potential function. Let's go ahead and go back to the problem here. This is our field. So here's another way you can compute this function. This is sort of like a shortcut. So what you want to do, so again, we know this is equal to partial of f respect to x, partial of f respect to y, partial of f respect to z. So that means to find little f, we can integrate each component respect to x, y, and z respectively. So I'm just going to go ahead and do that. So you will integrate the first component 2xy respect to x. Then you're going to integrate the second component, which is x squared plus 2yz respect to y. And you're going to integrate the third component, y squared respect to z. So if I integrate the first piece respect to x, I get, so the 2 will cancel, you got x squared y. Hold on to the integration constant plus c. And this is, if I integrate the second piece respect to y, I get x squared y plus respect to y. So that'll be y squared z. Hold on to plus c. We'll tag that along at the end. And then for the last piece, we'll have y squared z. All right. Now your potential function, f of x, y, z, it's going to be the combination of all of these. So you'll have this piece. So you need x squared y. And now you're not going to use this again because we already have it, so we don't need that. And then this piece right here plus y squared z. And then this, but we already have it, so we don't need to repeat. And now we put in our integration constant plus c. So that's the quicker way to get to the potential function, which is exactly same as here, the way we did it by taking integral at each piece, setting it to the partial derivative. Okay, I hope this helped. Take care.